Hello and welcome to the 14th class on coordination chemistry. Yesterday, we spent time only on revising the CTS, mostly charge transfer spectra and the color properties, and we did nothing. So today, we shall be a bit of revision. After a bit of revision, we will be discussing the stability of complexes. So I had given yesterday, supposing I'll tell you to draw the CFT, predict shape and magnetic properties. Say, if you FeCN pole 6, 3 minus. You have to use CFT to explain the number of unpaired electrons, or it is diamagnetic, you say that, and also tell me whether it will be a less complex or HS complex. And also you calculate the CFSE, crystal field stabilization energy, depending on its Fulak. Welcome Fulak, Mr. Fu. Are you able to see my screen?
Yes, sir.
Yes, you must be thinking why you are delaying, because we have only 1 hour time today. So better let us do simultaneously together on a friendship basis. We'll do. Okay, that also admit. This is ferric plus 3 ferricyanide, and it is 3D5 configuration, because iron is 26 4s2 3D6. Ferric is this will go and one electron will go, so it will be 3D5. So once I talk of CFT, there is no hybridization, nothing. Simply splitting off the d orbital in the octahedral field, the T2G remains below, and EG RS. You thought that there will be no class.
Yes, sir. Sorry, sir.
Stand up on the bench. Okay. Listen, we are trying to read the kundali of the entire information about this complex ferricyanide. And we have to use the CFT, crystal field theory, where we found that this is ferric 3D5, and in the isotropic field, that means without any splitting, without any ligand field, it is D5. I'm so sorry. D5. Hund. 5 unpaired electrons. But because cyanide ion is a strong field ligand, a very, very strong field ligand, and not only that, it is a pi acceptor ligand. At in the spectrochemical series, its position is almost at the end, and therefore it will form a less complex. All these 5 electrons will be first filled by T2Z, and then if at all there will be any excess, then that will go to EZ, which will not happen because only 5. So hund, then poly. 5 electrons are now accommodated in the T2G set, leaving behind only one unpaired electron, but there has been a great reduction in the number of unpaired electrons. So it is an LS complex. and it is paramagnetic. I have asked you to say whether it is para or dia, and on number of unpaired electrons is 1. You can also find out what is the spin magnetic moment by the formula n into n plus 2 square root, that is 1 into 1 plus 2 square root, that is root 3. It is 1.732 Bohr magneton. So looking to the shape is octahedral, there is no doubt about it. Once it is 6, it is octahedral. But the question is whether it is LS or HS. It is LS, low spin complex, because cyanide ion is a strong field ligand. Magnetic property we have done. We are left with CFSC. CFSC, you calculate CFSC. First, this is the energy, total energy of the ligand field and the energy of the isotropic field. Well, there is only here the number of unpaired electrons. But here, there is no number of unpaired electrons here. So this will be totally removed. There is no unpaired electron, so there will be no cancellation of electron pair. So there is no electron pair. I'm so sorry. There is no electron pair. So there will be no cancellation of electron pair. So how to do the number of electrons in the T2G EG set, and this is above this 3 by 5 del O. This is below minus 2 by 5 del O, that you know. So in terms of del O, supposing I give you del O, write down 35,000 centimeter inverse. Write down. So you find out in terms of centimeter inverse. If you are asked to find out in joule, you can also find out in joule. Supposing I give you the data, cyanide ion in this particular complex has a split with this high value of, I don't know whether it is the real value, but I am giving a fictitious value for calculation. And then we first find out in terms of del O, and then we will give the value of del O. Then we see plus 3 by 5 into number of unpaired electrons, number of electrons is 0 in the EG set into del O. Minus 2 by 5, all the electrons are present in the T2G set. There are 5 electrons into 5 into del O, plus the number of electron pairs. There are 2 electron pairs, so 2. And let me give you the pairing energy value. Let me give you 21,000. That is why del O is greater than PE. It will form a low spin complex. So 2 into pairing energy. So we'll be adding this, substituting these values later. So this cancels. So we remained with 5 get cancelled. So we have minus 2 del naught plus 2p. So this minus 2 into 31,000. We will find in terms of, and this is 21,000. So what is the net?
So del O 35 আছে 35,000.
Sorry, 70,000, and this is 42,000. So it will be definitely minus. It will be a stable complex. Today we'll talk about stability. Has to be either minus or 0. Cannot be plus. If it by chance it becomes plus, it is unstable complex. So it is minus 60.
28,000.
And if you are asked to find the energy in terms of joule, then energy is Hc nu bar, that is 6.626 or 627 10 to the power minus 34 joule second into 3 into 10 to the power 8. Oh, this is centimeter. Let us make it 27. Erg into second, 3 into 10 to the power 10 centimeter per second and nu bar is, 28,000. So you need not give the negative sign. The negative sign means stability. That much of energy has been lost with respect to the barycenter. That's it. So when you calculate energy, don't put negative sign. There is little meaning. So whatever will come in erg, then you divide, supposing it comes in erg, so you just divide by 10 to the power 7, that will become joule. Or you can convert into meter inverse and then put it in meter inverse. You are expert in mathematics, and so I need not tell you the Oriya version of that, because we are uh, recording, and this will be used maybe by others. Shall be little civilized in our discussion. And then if I ask you one more question, why the color of this compound, this particular complex is uh, yellow, for example, I'll tell. How to explain the color of this? What could be the reason for this? Red is red color. So tell me what could be the cause of the red color of the ferricyanide ion.
Say DD transition.
This is not the Turnbull's blue or Prussian blue, whose composition is same, but their preparation methods are different. It's not that. It is ferricyanide ion. We find it in the form of a salt, potassium ferricyanide. Potassium ion doesn't have any electron or anything to play, has any role to play in the color properties. So it is only the complex. So there can be two possibilities. One, cyanide is a very strong field ligand. So, and it's a pi acceptor ligand. It is very, and iron is in the +3 state. It has got still many more electrons, 5 electrons to donate. And it has, cyanide ion has an antibonding uh, backend pi orbital to accept. So there can be MLCT complex. So the CTS possibility is large. But since the color is red, we have to explain that, red, if it is really red, then what is the complementary color of red? If you draw, what is the
Green.
complementary?
Green. Green.
Green.
Green.
So V, I, we cancel V, B, Z, Y, O, R. So it has to absorb in the green region. I mean, its tail, since it is really very uh, promising red color, then it cannot be due to DD transition. Of course, DD transition is possible. Of course, DD transition is possible, but this has to go with this same spin. Thus, it has to violate the spin selection rule, and as such, DD transition is partially allowed. And moreover, it is spin forbidden. It has to break down the spin allowedness, partial breakdown of both spin selection rule and Lapote L selection rule. Therefore, the intensity of will be very, very small. So what strikes to my mind, it is due to the fact that the absorption is such that it is falling towards the tail is coming towards the green region here, and therefore we see the red color. So without any delay, I think what the guys are saying, guys, so DD transition, you know, this is ferrocyanide. I'm talking of ferrocyanide, they're talking of DD. If the ferrocyanide is DD transition, ferrocyanide also the D transition, they are saying, no, the DD transition, nobody is saying. About colored, nobody is saying. They are ultraviolet colored. So this guy is writing most phenyl group, potassium hexacyanide of this guy is a Hiromarka guy like us. Hexacyanide is writing. The color we observe is yellow. I'm talking about, he's talking about ferro. So the absorption must be in the complementary blue violet, indicating relatively a large energy difference. So that is saying, but it is not saying whether it is due to DD or due to, so cause of color is possibility of electron transition from a lower to higher orbital. If that transition is equivalent to a photon, oh, that he is trying to kid us. But I am not in favor of a DD transition for both ferro and ferric. Nobody is. No, nothing about color. The cause of color. Nobody will tell. Right, this. The color of ferricyanide is indeed due to charge transfer spectra, specifically metal to ligand. Of course, I told you that MLCT is most dominant in all cyanide carbonyl complex, but the possibility of the other is not ruled out. But since there are so many electrons in ferrous and ferric, ferric, there is one unpaired electron, whatever it may be, there are 6 in ferrous and 5 in ferric. So the possibility of MLCT is more. Move from the iron to cyanide ligands, causing the characteristic red color of the fire. No, it is absorbing in the green region. I mean, it is not absorbing. Most of them, it is falling in that region, in the UV region and the near UV region. So that a lot of portion is falling in the visible region, lot of portion. And the most portion is falling in the green. So it is looking red. So the Vedantu is the intense color Prussian blue. Prussian is not due to associated transfer of electrons from ferrous to ferric. Oh, see, it is talking about IVCT. We are not interested. Now, you must be thinking that we are spending so much of time for this. But anyway, this explanation is correct.
सर
Yeah.
सर LMCT तो सर बेसी फेवर है वो तो काहे
Why?
हाई
Sign
ऑक्सीडेशन स्टेट ऑफ Fe3 प्लस अच्छे
well, and also there is another point. There is another point, high oxidation state, and as well as less number of electrons, either 0 or limited number of electrons. But this is 5 electrons, 6 electrons. Plus 2 plus 3 is not so very high, like chromium plus 6. So we don't rule out the possibility of LMCT, but the MLCT is definitely a greatest possibility because it has got 5, 6 unpaired electrons. I mean 6 electrons or 5 electrons, as the case may be. And the pi acceptor ligand has very good antibonding vacant orbital, pi star orbital to accept, right?
Yes, sir. ସେ MLCT ଟା ସେତେବେଳେ weak intensity ହବ?
No, all CTAs are very strong absorption, and also the color is also very intense, right?
Yes, sir.
Whenever you find cyanide in your examination or carbonyl complex, it is giving color. Most of them are colorless, but ferricyanide, ferrocyanide, they are colored. So, and most of the zero nickel tetracyanide, nickel zero, these are there are a lot of electrons. No, it's not D10, it is D8, 4s2 3d8. There are 10 electrons, 4s2 3d8, if it is nickel zero. So the MLCT that comes, that is a colorless. Most of them are colorless, and some of them are really yellow. Yellow color of ferrocyanide can be understood. Ferrocyanide is yellow, indicating that the tail is protruding to the violet region, and therefore we are getting yellow. But this is red, and therefore it is protruding more. And it is color is intense, not light. So let us go for another one to find out everything we have done. Say, the question number 2, apply CFT to predict, first predict the shape and use CFT to find the magnetic properties. And find the, I will not ask you to find CFSE. For some reason, you will know after some time. It will be really very time consuming. We don't bother to find. I have given in my file how to find the CFSE for all types of complexes, including square planar. Okay. So tell me what will be the, since the coordination number is 4, there are two
SP.
possibilities. There are two
SP.
possibilities. Either it will be tetrahedral or square planar. Somebody was saying SP, Krishna. Yes, it is SP because 3D metal ion with strong field ligand, it will be SP. There was one exception where 3D metal ion with a weak field ligand was almost square planar. It may be a truncated or a distorted tetrahedral, but mostly it is square planar. Can you tell me which 3D metal ion and which weak field ligand will give you square planar complex that I told you? Yes.
NiCO whole 4 2
No. NiCO whole 4 is a tetrahedral complex.
Sir, CuCl whole 4 2 minus.
Yes, Udit is correct. CuCl42 minus copper in the +2 state, D9 configuration, and you expect, since it is 3D and cyanide, chlorido is a very weak field ligand, everybody will suspect to be a tetrahedral, but actually it is square planar, because we shall study in another a couple of days. We will complete this program and go for the transition metals and P block in a different style. No recording, I mean oblique recording will not happen in those classes. This I will upload it to complete, because many interesting lectures are coming. Jan-Taylor effect, JTS, Jan-Taylor distortion, JTD. I'm sorry, JTS, no, it's not JTS, JTD. and also I'll tell you molecular orbital theory or ligand field theory. At least I'll give you a brief idea with some examples how the crystal field aspects as well as the covalent bonding aspect, the molecular orbital, the overlapping, including pi bond, everything will be amalgamated, and the splitting is also there. Everything is a khichdi. That theory proves of far better than CFT to explain all the properties explained by CFT and as well those which cannot be explained by CFT, like bonding, like why the spectrochemical series has happened like that. Why the iodide is a weak field ligand, why water is a intermediate field ligand, cyanide is a strong field ligand. So all these whys will be explained by a motive. Okay, so this is a square
They're
planar complex.
diamagnetic.
And since it's nickel in +2 state, it is only 3d8, and once it is 3d8 and we are asked not by VBT but by CFT, our uh, splitting pattern will be different. You know, the two Z carrying orbitals YZ and GZX will be below, and DXY will be superseding the DZ square, and DZ square of the upper part will be coming down, and far above is DX square minus Y square. So this is the splitting pattern which has happened due to severe tetragonal distortion leading to complete removal of the trans ligands, Z out distortion. And therefore, this gap is actually Delo. This we call Delo. And these are small, small gaps. So the 8 electrons will be filled up. First, these 4 orbitals up to dxy using the Hund's rule and the Pauli's exclusion principle. Hund, then poly. So 2 plus 2, 4, 4, 8. Because this gap is very large, greater than pairing energy. So these are smaller than pairing energy. So all of them 1, 1, 1, 1, then 2, 2, 2, 2. Then we are not left with anything. So it is paramagnetic.
Yeah.
Yes.
Diamagnetic.
Sorry. I'm so sorry. It is diamagnetic. Unpaired electron is 0. And if somebody will tell you its color, then you have to explain well, it is colorless. It is colorless. And this colorless, it is saying it has got a general belief that if it is colorless, then the DD transition will fall in the totally UV region, no leg. But it's untrue. Although it's untrue, this answer is unacceptable because square planar complex lacks the Laporte allowedness, as well as because the octahedral and square planar complex, which has a G symmetry, that DD transition is forbidden, but partial breakdown occurs for some reasons. I didn't like to waste my time. That makes and how do you know that DD transition? Yes, it is possible because there is one electron. One electron from this can go to the vacant dx square minus y square. So there is a homo-lumo, highest occupied. Of course, homo-lumo, that word, that term can be applicable in MOT, I mean ligand field theory, not here because this is simply crystal field theory. So from the lower to higher there is a possibility, but that transition is almost forbidden. But there is a possibility that cyanide ligand has a pi star antibonding orbital and so many electrons are there. So MLCT complex that falls in the UV region, so it is colorless. If always you say that DD transition बावजूद, despite DD transition it is colorless because it is falling in the UV region, then why some D10 configurations, D10, D10 as well as D0, they are colored slightly yellow color, some cyanide complex, that hexacarbonyl chromium 0 is yellow. It is D0, I mean, of course, it is chromium 0 means it is D6. D6, 4s1, 3d5. All electrons are there, so why it is colored? Is it due to the DD transition? Because there is electron in the D and all the 6 electrons can be put it, you know, because hexacarbonyl chromium complex is diamagnetic. If you remember in VBT, all the 6 electrons were being paired in the 3 d orbitals leaving behind. Even the 4s2 electron, 4s1 electron was coming and to pair all the 6 electrons in the 3 d orbitals and making room for dz square and dx square minus y square. For the d2sp3 hybridization, it is octahedral and it is diamagnetic. How can you explain in the CFT? These 6 electrons have to be there in the T2G set. In the T2G, all the 6 electrons, now including the 4s1, all will come to D. That 4s1 will come to D and it will be all arranged in the dxy2, dyz2, dzx2. So T2G6 and that's the thing. So I don't agree that DD transition is falling in the UV region. So that because generally it is told that why CuCN, I also told you in the beginning, while I introduced CuCN whole 4, 3 minus is colorless due to it is D, it is +1, D10 configuration, there is no room for any DD transition. But CuCN whole 4 whole 2 minus is D plus 2 and it is D9 and there is a possibility of DD transition. Even if you show the SP square planar geometry here from dxy to dx square minus y square, there can be a possibility. But we were saying in the beginning that this is colorless because all the the absorption peak is falling. The absorption takes place in the UV region, so we don't get any color. But now later on I rectified that absorption is mostly the CTS absorption and DD is there. In this case, DD is there, but that is buried inside the strong CTS peak. But you might be wondering that in the examination, what shall we write? You don't worry. If there is such a bit for comparison, there is CTS falling in the ML CTS falling in the UV region, DD transition falling in the UV region, both will be there. Then you will be selecting and also both will be there. I mean, multiple correct answers. So both are correct. That is falling, that is there because D9 में जरूर होता है DD transition. D10 में DD transition नहीं होता है. इसमें CTS होता है. CTS UV में पड़ेगा. D10 configuration, you know, that one electron can go to the metal ion sorry, to the pi star complex of the cyanide ion. So MLCT is possible. That's it. Usually in zero oxidation state, it happens. Lot of electrons, d electrons are there. So MLCT. So all these things we have already discussed. So we will not spend more time. But in a acha, it is colorless. You can write for your examination purpose, board purpose. If it is colorless, then DD transition is falling in the UV region, so it is colorless. But you know the inner story behind it. D9, there could be a DD transition. Had it been Cu +1, then there is no DD transition. So if somebody asks a question why it is colored and why it is colorless, you have to answer in terms of CTS. Why it is colorless? Better answer if it is board, there is no DD transition. It is board, no DD transition for D10 and D0 in board examination. But if it is colored yellow, still it is D10, then you will say it is due to CTS, and a part of it, a leg portion is falling in the violet region, and we see the complementary yellow. So everything you know, you are now Hero Marka, but you have to study. You are not doing the extent to which I have loaded with information. You have to study, and I have not given the homework, the practice question. I will give you so many practice questions, and in any standard book for the NEET and IIT Advanced, you will find so many questions, and now you can answer with confidence. Well, today we shall be taking up stability of complexes. Now, we'll write in a later time because we are having paucity of time. Is 5:42. But on this day we have a complete 1 hour program. We started at 5, so we can go up to 6. Sometimes we go for 1 hour 15 minutes. So we'll do that. It is being recorded. There are two types of stabilities: thermodynamic stability that deals with the formation constant or stability constant. It is thermodynamics, delta G, entropy, change in entropy, change in enthalpy, change in free energy, giving you equilibrium constant. That equilibrium constant is called the formation constant of the complex or stability constant. But there is another stability called lability that pertains to the kinetics, how fast a reaction of that complex will occur, particularly with respect to substitution reaction. How fast another ligand can substitute the present ligand, that is generally taken as the study of kinetics. So the two are not always go hand in hand. There is no fixed correlation. A thermodynamically very stable complex with a high formation constant may be very labile. I mean, it will react very fast. If a certain complex reacts very fast, it is called a labile complex for a particular substitution reaction. And if a complex doesn't react or react very, very slowly, then it is called an inert complex. So thermodynamically, it may be very, very stable. It may not be an inert complex. It may be a labile complex for some substitution reaction. Maybe thermodynamically, it is a very unstable complex having a very low formation constant. Backward reaction is more favorable. Forward reaction is less favorable. The equilibrium constant might be very less formation constant. But still, that reaction at that particular complex, once you isolate it, get it, it may be very, very inert. It will remain for days together and it will not change, or for any substitution reaction, it will be inert. So, but usually stability means thermodynamic stability, but we will explain both. Many of the factors, they are same. Particularly, the kinetic stability doesn't depend on the nature of the ligand which will come. to substitute. It is dependent mostly on the metal ion, the property of the metal ion, whether 3D, 4D, 5D, its oxidation state, and the number of d electrons. And the number of d electrons, where it is, how many, T2Z, it is symmetrical or some, or EG set, there is some unpaired. Or so these things are taken into consideration. But thermodynamic stability takes into account both the metal ion factor as well as the ligand factor. So let us first study the points. Uh, I was telling you this complex is tetraamine diaqua tetramine copper 2 complex. It has a high formation constant, 1.2 into 10 to the 13, high formation constant. So thermodynamically, it is highly stable, but it is extremely labile complex. The blue color, its blue color immediately changes to green when you add a little bit of conc HCl. So all these ligands are substituted by chlorido, and it forms a green tetrachlorido cuprate 2 complex. On the other hand, hexamine cobalt 3 plus also has a very high formation constant, but that is really not. Here, there the two go parallel, but here these two cases, I mean, these two complexes, one is copper complex, the cobalt complex, one having high stability constant but labile, but this having high stability constant but inert. So there is no fixed correlationship between the thermodynamic stability and kinetic stability or lability. Therefore, kinetic stability should be called lability. That lability includes inertness, labile complexes as well as inert complexes. The term that will be used for that kinetic stability should be lability. So for you, it will be, but I will be explaining factors for kinetic stability at the end. But first, thermodynamic stability. So what does it mean actually? The formation, actually, it's a stepwise reaction. What I am writing M, actually, it is aqua complex. Whenever you have a transition metal salt solution in water, for example, ferrous sulfate, you add in water, immediately it will remain in hexaqua iron 2. And you want cyanide complex, then you add KCN, then aqua ligand will be substituted by cyanido ligand in a stepwise manner. You can also find out the stepwise formation constant. So you know this is the first step, second step, third step, and there are n number of ligands. N is 6, coordination number is 6. And when you add, all these stepwise intermediates will be cancelled, and you are having overall reaction that supposing you are adding excess of ligands. In one stroke, you are getting your hexa coordinated or your n number of ligands coordinated, finally you want it. So that is the overall formation constant or simply formation constant or stability constant, which is the product of all the k values. As you know, when the equations are added, the k values are multiplied. So this kf is the overall formation constant, and very interestingly, you find the k values, the probability of replacement will become less as more and more ligands will be there from outer side, less ligands of the aqua ligands will be there. So the probability factor will be less and less, and it has been found that there is a slight decrease in the stepwise formation constants of higher orders. I'm showing you an example where we want a tetramine complex, because D8, D9, D10, if you allow them to act in its own way, they will go for 4. But that doesn't mean that copper 2 plus will not give a hexa coordinated compound. That we will see in our program of Jan Teller distortion, that all copper 2 plus hexa coordinated complexes are distorted octahedron, where 4 will be lying in 4 corners of a square with the distance less, and the other two which are in axial positions, they are little stressed out, stressed out with, thank you, having a greater bond length. So why D9 configurations, they are very gullible for the Z-out distortion or Zahn-Teller distortion, that we'll be knowing when we study ZTD. Hello and welcome. This is decaf. What is happening nowadays, because we are having classes in the morning and you guys are really busy, you have otherwise when we have our class in style with 2 hours in hand, with maybe 10 minutes for chatting and I mean arousing a lot of fun and humor, sometimes going a little uncivilized, not unparliamentary, uncivilized. No, this is really you are trespassing your jurisdiction. You know, in uh, earlier times, you were scared to come to my class, right? When you are seeing that JJ was taking class, then you are going away from the door itself, right? But nowadays you are so carefree that you are confidently entering into my class. Why? Answer. My students want to hear. Hmm? Because you want to see my students, right? So in that guise, in that pretext, you are trying to sabotage the class, right? Yes, you American guy, you go. Let me finish and I will play with you, okay? No, you Sasa, take your princess. Please, I'll go another 10 minutes. Okay? You are a good girl and a big girl also. You close the gate, close the door. And you are nosy. Please blow and use your uh, tissue. Close the door. Yeah, close the door. Oh. Now see, these tetramine copper is a square planar complex, but when you prepare, you can gradually find the different complexes. Triaquamine and its formation constant, it is 10 to the power 4.22, log K1 is 4.22, and then second one log K2, log K3, and finally all you can measure. While you go slowly, you can measure to what extent it is going. And finally, if you want this complex, I told you that if they are given a chance, they will remain in tetra-coordinated form, D8, D9, D10. But they can also give hexa-coordinated, particularly D8 and D9. D10 is very rare possibility. That we will know because that is totally D10. So the overall formation constant is the product of all this. So it is coming 1.2, 10 to the 13. That value I gave you there, showing you that this is so highly stable thermodynamically, but when you add a little conc HCl, this amine will go away. This is the case. I took this one. I took maybe this one. I took this one, but you can also take this one. This is such a high formation constant. This is called the formation constant. And log Kf will be a log of this, not minus log of this. It will be nearly 13 point something, something. So here I have given a data formation of this hexa-coordinated. This is a hexa-coordinated copper complex where the two water will remain in axial positions, little jet stressed out, a highly distorted octahedral complex, copper 2 plus. But the earlier example I was talking of, the square planar, tetra-coordinated, but this is hexa-coordinated. We started from CuH2O whole 6. Then gradually 1 ammonia, 2 ammonia, 3 ammonia, 4 ammonia. See, here is another friend of hers, Zia. I call Sia. Her name is Kathy. We have given her name Kathy. So Kathy, Sia, and me, we are good friends. Sia is my best friend. Take. You take. How dare you? You close the door. Now, the reciprocal of the formation constant is called the dissociation constant or the instability constant. And we have done a few problems in ionic equilibrium, formation constant, and then the opposite of that is the dissociation constant. So if the formation constant is high, then the dissociation constant is low. The opposite reaction is very, very less likely. Now, the factors. I will tell you within half an hour, I will cover all the 7 points, 7, 8 points, but I'll give you a note, little bit note next time, not today, but you hear very, very mindfully. Now, size and charge of the metal ion. More the charge, magnitude of charge, less the size, the charge density will be more, and therefore it will have a greater power to attract these ligands and form bond. Again, we are coming to MOT or at least VBT and bypassing CFT. So this is a very khichdi type of thing where real factors which are responsible we are discussing. Some factors are applicable for some complexes, some other factors will be applicable for some other complexes. So all the factors we are discussing, right? So don't talk about CFT or MOT. So we are only considering which factors will make the KF very high. Most of the thermodynamically stable complexes are inert, most, but not all. There are many which are labile, and that also is very complicated. Maybe labile with respect to some ligand substitution reaction. It may be inert for some other reaction like isomerization, for like other type of reaction. There are so many types of reactions that a complex can undergo. Isomerization is one of them. So usually the kinetic stability is taken for the ligand replacement reaction. It's very complicated. The lability and the inertness should be specified to a particular reaction, and that too the ligand substitution reaction or displacement reaction. So look to the formation constant. Ferricyanide, ferricyanide is much more stable thermodynamically. Oh, what is happening here? Okay, because this is +3 and size is less, sone pe suhaga. More is the oxidation state, less is the size, same element. So this is Fe2 plus. So it is 10 to the power 31, while ferrocyanide 10 to the power 8. Both are highly probable, but still ferricyanide is thermodynamically more stable. Similarly, beryllium tetrahydroxide is more stable than tetrahydroxide this 10 to the power 7, because beryllium 2 plus has much smaller size than magnesium 2 plus. Here, this is very important for higher level learning. Usually when we look to 3D metal ions and you put it in aqueous solution, they will form aqua complex, and you are carrying out some other complex formation, and you are trying to measure Kf, stepwise formation constant, and then overall formation constant you are trying to. So aqua, this is the order of the stability of complexes. Aqua, hexa aqua complexes, which are high spin, because +2 charge all are, including cobalt 2 plus, it is a weak field metal ion. So aqua is an intermediate field. So all of them will give uh, uh, high spin complex. T2G and EG will be 1-1 occupied. Then pairing will start from T2G. We didn't get time to revise many more. So since the 3D metal ions, all +2, all hexa coordinated, all high spin, because you have taken aqua ligand, and +2 is a very weak field metal ion, so they will form high spin complex. So Irving and William, they have found a very interesting series. Most of the books, they start from manganese, but we start from the beginning. Scandium +3 is there. Only oxidation state, as we shall revise in our transition metal chemistry, that scandium has only +3 state. It doesn't have variable oxidation state. So there is no, because we have given, or not we, Irving William have given the order for +2. So there is no such compounds for scandium 2 plus. Then we have given from titanium. Since the size decreases for metal atoms, there is some, irregularities. First decreases, then remains constant, then towards the end it increases, that we have studied. But for +2 ions, there is a gradual decrease in the size from scandium 2 plus doesn't exist. From titanium 2 plus to Zn 2 plus, all 2 plus, there is a decrease. So since size decreases, then the polarizing power increases. I mean, the charge is constant, size decreases means the charge density increases, so the stability of the complex will be more. But that is complicated by the crystal field stabilization, CFSC. As we have calculated today, we have revised that in D6 configuration, high spin complex, the numerically highest value, I mean, the graph falls to the minimum point, means numerically highest, most stable complex, it has D3, and then again increases. Manganese, it is 0. This crystal field D5 configuration is 0, and then in D8 it is again the lowest. So that is the trend that we receive from CFSC. When I goes down means stability increases, goes up means stability decreases, and when it becomes 0, CFSC becomes 0, stability is minimum. But that is one added concept. But the main idea that you should not forget, that in a series the size decreases. So there is definitely an increase in stability. But that increasing stability due to decrease in size is marred, is complicated by CFSC. So there must be a hill somewhere. But the trend is increasing, but there will be some hump. We expect a hump at D3 configuration, chromium. D3 is chromium 3 plus. Chromium 0 is 4s1 3d5. Chromium 3 plus is 4s0 and 3d3. 2 electrons will go, 3 will be there. So chromium should be on the top. Yeah, chromium D3. D3, we are talking of chromium 2 plus. Chromium 2 plus is D4. So vanadium 2 plus would be at the top. Vanadium 2 plus is 4s2, 3d, 3. So 4s2 will go, 3d3 will remain in V2 plus. So that should be at the top. But chromium 2 plus is at the top. By mistake I told 3 plus. We are all considering in the Irving William series, we are considering 2 plus. So chromium 2 plus actually sits on a hump, not vanadium 2 plus. That you must bear in mind. And then it increases, and manganese actually is falling down. CFAC wise, it is 0 CFAC, and therefore manganese 2 plus is not only gives weaker aqua complex, hexa aqua complex than chromium 2 plus, but also than Fe2 plus, because from manganese again the CFAC decreases. Decreases means stability increases. I mean the magnitude increases. And then finally D8 maximum. So nickel 2 plus would be the highest in the other side. There must be an increasing trend because size is decreasing. But nickel should be at the top. Then it should decrease in copper and zinc. But ironically, copper 2 plus is at the highest in the plus 2 metal ion, 3D plus 2 metal ion, aqua complex, HS complex, any HS complex. The most stable one is copper 2 plus. I was harping this point again and again that copper 2 plus is D9 that has got a severe Jan Taylor distortion effect, ZTD effect. Don't go anywhere. Yes, you have a tuition, yes, because I'm recording this. So nickel 2 plus should be at the top of that should be in a hump because it has got the graph wise it is the lowest, but since we are not taking the negative value, we are taking the actually how much stability has occurred. So it is at the minimum point, that is the highest stability. So it should be on the hump, but actually it is not on the hump. It is the copper 2 plus which is on the hump because D9 has the highest ZTD. And let me tell you, the chromium 2 plus having D4 configuration in high spin, we will know that it will be Hund, and there will be another Hund at the upper D4 configuration. And there you will find the ZTD is there, but a very small ZTD effect. Chromium 2 plus is D4 configuration. And in high spin complex, Hund. So you will know that both chromium D4 high spin and D9, there no high spin, low spin word is applicable for D8, D9, D10. So D9 and high spin D4 has a ZTD, and ZTD is very minimal in chromium 2 plus, that is D4, very high, severe in D9. We'll know the reason why. Therefore, copper 2 plus is highest. Zinc is below that. It's supposed to be below that, but CFSE wise it is 0, but size wise it is minimum. So it has to, zinc has even lower than nickel 2 plus. Zinc 2 plus stability is even lower than nickel 2 plus because nickel 2 plus has D8 configuration. CFSE factor will help you, but Zn2 plus CFSE factor will not help. Only the size factor will help. It is the reduced subset chota size. How do you find? So this is the series titanium 2 plus less than vanadium 2 plus. Chromium 2 plus is sitting at the hump. It has not only greater than vanadium 2 plus, but also greater than manganese 2 plus. Manganese 2 plus has even the lowest stability, lower than vanadium 2 plus, titanium 2 plus, because it has CFAC 0, CFAC 0, and 0 factor. And you know, vanadium 2 plus should be at the top because of D3 configuration. I mean, should be at the hump. So it has got a stability factor, CFAC stability factor. In all these considerations, the size factor is not helping manganese 2 plus much, and therefore, yeah, you are getting the minimum stability of aqua complex is for manganese 2 plus. So this is the Irving order. I have already explained to that. Then the second point, these things will be consuming about 10 minutes. All other things. Stability of metal ion, I have already told you 3D gives Delo minimum, 4D, 5D, more and more. So the reason also I have told you there, just have a look. So it depends on the metal ion, the series to which it belongs. Since delta O increases, del O increases or splitting energy increases, so the CFAC also increases numerically, and hence stability constant also increases. So I have given an example: cobalt, rhodium, iridium. The stability of iridium complex is maximum, and oxidation state remaining same, and the ligand remaining same. Then ligands. If a ligand is appearing at a higher position in spectrochemical series, it is a strong field ligand, then it will definitely form a more stable, thermodynamically more stable complex. For example, fluorido ligand is more stable, is a strong, relatively, it's a weak field ligand, but spectrochemical series tells you that fluoride ion comes later than I minus. I minus is in the beginning. That means it is the weakest. So Delo is little more for fluorido. Reason MOT. Therefore, fluorido complexes are more stable than iodido complex. So strength of the ligands in the spectrochemical series. Then base strength. This is a general discussion. Because all the Bronsted bases are also Lewis bases. Therefore, more is the base strength, more is its nucleophilicity, attacking power, and more is the strength of the bond, and hence the formation constant will be higher. Since cyanide ion is the conjugate of HCN, which is a weaker acid, so it is the strongest base, and water is the weakest, ammonia is the intermediate. So the cyanido complex is more stable than amine complex than aqua complex. So I am telling you the the uh, the methods, the factors that you will bear in mind while you are attempting to grade the different complexes in order of decreasing stability or increasing stability. But another interesting theory is HSAB theory, called hard soft acid base theory. Hard and soft acid base theory. That is a different theory. Neither it is Lewis theory nor Bronsted theory. It's something different theory, I'll tell you. But it is under Lewis. It is a variation of Lewis theory. ये खत्म नहीं होता. Turned into cold drinks. Sorry, guys. It means there are two types of acids, two types of bases: hard, soft, hard, soft. Hard acid, let me tell you that ligands are Lewis bases and metal ions are Lewis acids. They will accept electron and the ligands will donate electron. So when I'm talking about base, you think of ligands. So a hard base, a hard ligand is the one which has got smaller in size, so that they have very low polarizability. Think of Fajan's rule. So if it is hard, small in size, negative ion, or a small size atom like O, N, so it is not a large size, say sulfur, phosphorus. So it is small size atom. The donor atom is small, and it is like fluorido, even to the extent chlorido. Then they are called hard bases. And soft bases are those which have got high size. So their polarizability will be more. They have a greater tendency to form covalent bond. Hold on. So I'm not talking about the the Fajans rule. So iodido, sulfido, these are I've written, and some which are having pi bond, carbon monoxide, cyanide, pi acceptor ligands, even small size but hydrido, it is considered to be a pi, pi acceptor ligands, as well as the small large size ligands like sulfido, iodido, bromido, and that includes ironically this the hydride ion. Hydride ion is not small, although hydrogen atom is small. Hydride ion is bulky. I think we did discuss during our size. So that has been considered to be a soft base. And similarly, we talk about the metal ion. Think about acids. A hard metal ion, hard Lewis acid, is the one which has got uh, smaller in size. Same, high charge, smaller in size, so that it has got high polarizing power. And a uh, soft metal ion, soft Lewis acid, is the one which is bulky, 4D series, 5D series, a bulky having low oxidation state, so that its polarizing power is less. And the HSAV rule says is very funny and beyond any question that a hard acid metal ion will form a more stable complex with a hard base ligand, fluoride. Fluoride will form a stronger complex with a 3D metal ion like Fe3 plus than iodide ligand. Hard, soft. A hard metal ion, Lewis acid having small size, high charge, will form a more stable complex with a hard ligand, which is a Lewis base, like iodide, like fluoride, aqua, than with iodide, bromide, and sulfide. Similarly, a soft Lewis acid or metal ion like 3D, 4D, 4D, 5D, and other metal ions. I have shown you here that hard acids here. The hard acids are high charge, small in size, titanium 4 plus, chromium 3 plus, chromium 6 plus, 3D series. Soft Lewis acids are large in size, like platinum 2 plus, palladium 2 plus, silver plus, gold plus, Ag2 plus. These are 4D, 5D. So they will form a more stable complex than a big size, a big, hati, homeopathy, right? So, yeah, they say that if one will be hard and one will be soft, then they, for covalent character, if you think of Fazan, then it will form a good covalent character. It says such a thing will not happen, either ionic or non-ionic. This cannot be one high polarizing power with a hardness of the metal ion and softness, high polarizability. Such a thing will break down as per the theory, which works very well, but it lacks a little logic, I do admit. So I have no protest or to defend that, why the hard, soft, hard, they form less stable complex. Now I have given you example. Fe2 plus forms a more stable complex with chlorido, which is relatively softer Lewis base, ligand, than bromido. Chloride, they come under the hard category. So Fe2 plus is hard, 3D, and chlorido is taken as hard. But hard soft, Fe2 plus is hard metal ion, hard Lewis acid, and bromide soft Lewis base. So this will be forming a less stable complex. But platinum, if it is a soft Lewis acid, platinum 4 plus, then this chlorido complex will be less stable. But chlorido is a very hard ligand. So hard ligand and soft acid, not possible. It's a very unstable complex. But the platinum can form a more stable complex with bromido. Both are soft. Platinum 4 plus is soft as a metal ion, Lewis acid. Bromido which is soft as a Lewis base ligand. So similarly, amine tetramine nickel is more stable than tetraphosphine nickel. Phosphine is a large size, phosphorus is a soft base, but nickel 2 plus is a hard acid. Similarly, palladium being the 4D series is a soft acid that forms a less stable complex, but it forms a more stable complex with more stable, softer ligand, that is phosphine. So then most interesting effect which you get in the examination is the Quillette effect. Same coordination number, but if you have a bidentate, tridentate ligand, which are called chelating ligands, because they form cyclic complexes which are called chelates, their stability becomes more. I have given you an example. I told you the formation constant takes into account first the aqua complex, then you substitute one by one, right? You might be wondering, I told you, if given a choice, it forms a tetra aqua. Particularly the mad fellow Krishna always will think in that line. Why it is 6? Well, sometimes also copper can form hexa aqua. Given the conditions, it will form. But given no other condition, no other favorable condition to increase the coordination number, it will form tetra coordination. But hexa coordination is also possible, right? So if you find Kf is 10 to the power 8, but same nitrogen donor, same coordination number with the 3-ethylene diamine, tris-ethylene diamine nickel 2 is having such a high constant, greater than 10 to the power 10, factor of 10 to the power 10. Why? The entropy factor, because in the examination you are asked which factor is responsible, because these are thermodynamic stability, del G. The enthalpy change in both the reactions is more or less same, but the entropy change is significantly higher. Here there are 7 particles in the left side and 7 particles in the right side, but here there are 4 particles in the left side. Ethylene diamine may be a longer molecule, but it's taken as 1 particle. So there are 4 in the left side, but there are once again 7 in the right side. So there is an increase in the number of particles. So number of particles increases means the chaos, the entropy increases. Del S is more positive. Positive here, but del S doesn't change in the first case. So the entropy factor is the major factor which makes del G more negative, and the stability constant becomes more. So it is entropy driven, primarily entropy driven. So I will show you EDTA is a hexadentate ligand. It forms, one ligand will satisfy coordination number of 6. And its stability constant is of the order of 10 to the power minus 18, 10 to the power plus 18.8, more than this. It is because it is forming more number of rings, I will tell you later. But first, it is entropy driven. Had it been 6 plus 1, 7, 7. Here 1 plus 1, 2, and this will be 6 plus 1, 7. So entropy factor is the mean. First, Quillette effect. Once you get a question from Quillette effect, entropy driven. The other factors affecting Quillette effect. First, the entropy. But the other factors is size of the ring. Five-membered ring has been found to be forming more stable complex than 6-membered ring. But in the pair strength theory, in hydrocarbon, cyclic hydrocarbons, cyclopentane, cyclohexane, cycloheptane, cyclobutane, that pair strength theory is applicable for non-polar molecules. These cycloalkanes, they are non-polars, but these are polar molecules for which that Bayer strength theory will not be applicable. It has been found the 5-membered ring is having less strength and more stable. Hence, and the example I have given you, the same, hexa-coordinated complex with ethylene diamine, and this is TN, trimethylene diamine. So this forms a 6-membered ring, trimethylene diamine. This is ethylene diamine, forms a 5-membered ring, and you find there is a significant increase in the stability constant when there is a 5-membered ring. So the reason behind the organic cycloalkanes cannot be extended to this polar ligands. Again, the number of rings in the complex. More is the number of rings, even if the coordination number is same, more is the stability. Now, you know, skillet effect is entropy driven, also dependent on the size of the ring, of individual ring, number of rings. Now see, this copper is coordinated with, think it is nickel. I have copy pasted. So this is nickel 2 plus. Is coordinated with, uh, say, ethylene diamine. Here also it is ethylene diamine. There is a steric crowding here. I have chosen a wrong one to explain steric effect, which I have given at the end. But supposing this is NS2, CH2, CH2, NS2, 4 coordination number 4. Here also we have given coordination number. Here, no, coordination number 6. Nickel is going into an unexpected coordination number 6. The stability of this will be greater. Because diethylene triamine, one molecule has 3 donors. So 2 such diethylene triamine will satisfy a hexa coordination, or coordination number 6. But the number of rings from each diethylene triamine is 2. But in each ethylene diamine is 1. So the total number of rings here with the same coordination number 6 with 3 ethylene diamine is 3 rings. All are 5 membered. Here there are 4 rings. And if you go for EDTA complex, there are more number of rings, 5 number of rings in EDTA. And if it is DTPA, diethylene triamine pentacetato, there will be 6 number of rings. So coordination number remaining same. Each ring size remaining 5. And in all the 5 rings present in EDTA, you can count. This is 1 ring, this is 2nd ring, this is 3rd ring, this is 4th ring, this is 5th ring. All are 5 membered rings. That size remaining same, coordination number remaining 6, but the number of rings is maximum in EDTA complex. So EDTA complex is more stable, and then ethylene diamine, diethylene triamine, and then ethylene diamine. Everything remaining same, but the number of rings is more. Then finally is the macrocyclic effect. If I have already introduced the ligands can be macrocyclic. Macro, that means the ligand themselves are cyclic. So the cyclic ligands like crown ether, like cyclam, like the porphines, where the magnesium porphine complex, one of the porphine complex is chlorophyll, and ferrous complex of one of the other porphines is the the hemoglobin. These have a tremendous stability because these cyclic ligands, which are called macrocyclic ligands, they have a cavity size which fits exactly to the metal ion. So that gives added stability to the complex. So this macrocyclic effect, remember, is both enthalpy driven and entropy driven. Entropy increases, del S is positive, and del H becomes more negative. So सोने पे सुहागा, del H negative factor and del S positive factor makes del G factor more negative. So the formation constant becomes more. So that is called microcyclic effect. We have seen this is cyclam. This is entirely one ligand having tetra coordination is a tetradentate but cyclic ligand called macrocyclic ligand, and the effect is called macrocyclic effect to increase the stability much greater. So you will find that this is greater. I have not shown the stability of this complex. Having coordination number 4, the square planar complex is much greater than ethylene diamine, bis ethylene diamine, copper 2. And here another, this is a crown ether having 5 oxygen donors to sodium, although it's not a transition metal ion, but being a non-transition metal ion, it can form very stable complex with this 15 crown 5 crown ether, where the size of the cavity is very matching to the size of the sodium ion, not potassium ion. Potassium ion will need another crown ether having more number of oxygen atoms, maybe crown 6, 16 or 18 crown 6. maybe like that. So I have explained that microcyclic effect is entropy and enthalpy driven, and some examples are chlorophyll, hemoglobin, and some of the other examples I have shown. And steric effect, if ligand having some steric crowding hindrance, like NN dimethyl is there, on this side NN dimethyl, on this side NN dimethyl. This is ethylene diamine otherwise, but this is a substituted tetra methyl substituted ethylene diamine. So that will form a less stable complex because of the steric factor. The approach of the ligands to form a strong bond will be less probable than ethylene diamine having no such steric factor. Then surrounding conditions may be pH. If you change the pH, the some other reaction will carry out. Some decomposition, I mean, the stability might decrease or increase. The radiation, supposing you put a light, temperature increase or decrease. So other surrounding factors also affect the stability. So this finishes. And can you arrange this? I have unfortunately written the answer. Okay, since we have less time, I have given this trisethylene triamine chromium, all chromium complexes, all chromium plus 3 complexes, but different ligands. This is hexamine, this is bis diethylene triamine, and this is fluorido, hexachlorido, ethylene diamine. First, we have to see the Killet effect. These two produces Killet effects. All are nitrogen. Then nitrogen donor. This is nitrogen donor. This is nitrogen donor. This is nitrogen donor. Nitrogen donor remaining fixed because nitrogen bases are strong bases, stronger ligands. So let us bring this diethylene triamine, ethylene diamine. I mean, first between them, diethylene triamine will form 4 rings. We have seen 4 rings. This will form 3 rings, and therefore this is more stable than this. And finally, this will not form any ring. Only nitrogen. This is not a Killet because it is a monodentate ligand. So after completing this nitrogen bearing ligands, then this is Killet effect, number of rings, and all are 5' rings, but number of rings. Then coming to the hard soft bases. You know, comparatively, chlorido is a softer base than fluorido. Comparatively, although chloride, fluoride, they have both taken in my list as hard basis, hard ligands, but chlorido is definitely comparatively more having greater size than fluorido. So definitely chlorido complex will be less stable than fluorido complex. So this is the order. So we finish today's program, and tomorrow I will be giving you a short note on this. I will take and revise. I have not revised VBT. I have not revised any tetrahedral thing, CFT, also VBT, and also I will give you the notes on stability, thermodynamic, and also tell you at the end what is the difference in kinetic stability and what are the factors. These will have some flavor of Zahn-Teller uh, distortion effect. So the factors are very limited, metal oriented. So we'll discuss that more. So if you have watched, I'm not talking to you guys who are there in Zoom, but those who are watching in YouTube in a subsequent time, because I will upload no doubt and make it public. So let me know if you have liked it. If so, hit the like button, and if not subscribed, subscribe to my channel. Bye
सर
bye.
काली हेबो
कहीं काली कौन असुविधा की
ନାଇଁ ସେ କିଛି
काली करिवा काली साथ दवा ना माने before we start November, because November, maximum November, uh, Children's Day, up to that we will have classes. Then we will start packing, and some uh, people will, just like in India here also, this Saturday, my old students who were my students in late 90s, mid 90s, they are here established. They are some or all PhDs and all that. They are here working in some big companies and all that, in big positions. So we have met 2 to 3 times in different get-togethers, but they have invited me. One family invited all of the other Odia guys who were with me in my personal coaching, as well as there were my students in Ravensa. So at that time, so why I am saying this, because when up to 1st to 14th we will be spending time in the P block and the transition metals, and we'll try to finish before. If not, then we will resume in after 25th, the last week we shall finish, maybe analytical chemistry. Bye bye.
Thank you, sir.
Thank you, sir.